All right, I guess we can get started with the fifth talk in this Summer of Data seminar. We have Adhiraj coming all the way from Europe, from a lab that a lot of us are quite familiar with. He's from Tübingen, from Matthias Bedge's lab. Still in his first year.
Finishing my first
Finishing
year.
his first year, but already done a lot of incredibly relevant work in data curation, both on benchmarking. He'll show some of his work that's very relevant to that bench, and then on data curation by adaptive sampling, and he's also recently been working on the data congruence project. But today he's giving a talk on a couple of those projects that
Yes.
he has done so far.
Yes.
So we are very excited to have you.
Thank you
And
so much for having me.
for coming on the way.
Thank you so much again. Looks like I have big shoes to fill after the fantastic talk by Furhan. It won't be nearly as well established, but I'll try to do my best to maybe give some insights on a couple of data related projects that I've been doing, one for benchmarking and one for pre-training as well. So yeah, thank you so much for the introduction, Piyush. Maybe I should say a bit more about me, but yes, I'm from Germany in a small little town called Tübingen. I'm finishing my first year in my PhD, and I'm mostly interested in multimodal data curation. By multimodal, I mean right now I'm focusing on vision and text, like image and text, and I'm planning on expanding that to video soon and other modalities as it sees fit. Because when we do data-centric machine learning, we mostly really care about keeping the model space fixed and perturbing things on the pre-training and the evaluation side to see how well we can improve models and how well we can make sure to know what the capability boundary of models are by good evaluation. It comes first so that it helps. Yeah.
Exactly.
Awesome. Yeah. Okay. Then yeah. Cool. Let's begin. Right. As something that's been established in that bench this year itself, yes, evaluation is a data problem, and we were exploring this mid 2024 and early 2025, and it's a paper that we published at ACL 2025, and it's a benchmark that we like to call one bench. It doesn't stand for one benchmark, but that's how I would like people to get confused when they hear it for the first time. It basically stands for open-ended benchmarking, which means, and of course I'll be explaining it, is that when you look at evaluations as data points instead of data sets, that actually exposes much more about what your models actually are capable of. And it's an easier way to actually probe into your model capabilities and see where models fail and see where models beat other models and like what the capability boundary is. So this is a joint work, mostly all of it in Tübingen. And yes, it got published at ACL last year, and I'm very happy to talk about this briefly today. Yes. And I think most of us know in this room that the current benchmarking system is like kind of broken. There are many problems. I've just highlighted four of them here. One is that yes, when models get more and more capable, benchmarks get saturated. Most models tend to get above 90% on every single benchmark, and that's not a good thing because you need to see where models fail so that model developers know where to improve their models. The second thing is that benchmarks across the board are heterogeneous. What do I mean by that? Is that let's say one single benchmark could be an MCQ benchmark where you can have like correct or wrongness for a single sample, and that's aggregated across the benchmark to have your final numbers. But other benchmarks, for example, for image captioning or so, could be much more heterogeneous. It could be a ROC score, which is a decimal point number, which creates a reality where different benchmarks evaluate different things, and there needs to be like a different kind of focus on separate benchmarks to actually get the most value out of it. I can't see my screen. Yeah, but it's okay. There is a big problem on the single score collapse, is what I call it. People, like if you've ever seen a tech report from a big model developer, the first page is their paper title, abstract, and a big plot with a lot of bar plots. That is your condensed number for every single benchmark, and they try to claim they're better than other models just simply on one or two scores. That's not a good thing because you're condensing all the evaluations of many different samples on many different capabilities into like one number, which doesn't tell you much. And finally, once you know your evals, this has been a problem for a long time. People try to hill climb, or they do many different things, such as they try to throw in their test set into their pre-training, or they try to focus on specific tasks to optimize for that. And that's not very good for foundation models. So what we do need is more dynamic, more granular, and cheaper evaluation. So yes, now if you think of evaluation as a measurement problem, we decided to have like a very fixed setup for how we want to do evaluation. So you have a model space, you have a benchmark space. So your model space is a bunch of foundation models that do different tasks. We decided to split it into LLMs and VLMs in the past. It could go on to video LMs, it could go to 3D LMs, it could go to whatever VLA models. It's very flexible. And you also have data sets which we also split into LLM benchmarks and VLM benchmarks, and they need to interact in a nice way. And the problem that actually happens when you try to pool in together benchmarks, which is what we've seen in that bench as well, is that things start to get a bit tricky, which I'll talk about a bit later, and I've also hinted at before, is that there are many different metrics across different sources. A few that I've highlighted here are what we worked on, such as exact match on MCQ data, your ROC score, which is a decimal point, your numeric score, if you have VLMs or LLMs as judges, it gives a score from 0 to 10 or 0 to 100, or you can have human preferences where they prefer different outputs from different models. Now, what happens in this broad ecosystem of evaluation is that because the cost to evaluate models on these datasets are high, you might end up in a space where there's incompleteness, such as if you create a matrix of data points being your columns and your models being your rows, that matrix might have empty cells. What I mean by that is that there might be data points where models have just not been evaluated by the model developers because they didn't see a benchmark, or is just not standardized, which is, I think, a problem. And of course, it's not lifelong. It doesn't scale because you fix your model space, you fix your data space. So benchmarking systems have a kind of problem because they constantly have to reevaluate models as they come in or reevaluate models on datasets as they come in. So we thought of that problem and we thought of a solution. We thought of the evaluation problem as something similar to how elections happen. And maybe that's the next slide. It's not, but it's okay. There are a kind of evaluation protocol called ordinal measurements, where if you have two models, we consider them to battle on a data point. So if GPT-4 and Claude 2 are fighting with each other on a sample from MMLU, and GPT-4 and Claude 2 get the same answer, then it's a tie. If GPT-4 beats Gemini on another sample, then GPT-4 wins. If GPT-4 loses to Claude 2 on another sample, then Claude 2 wins. So there's like an infinite scope to scale up your benchmarks if you consider it as battles among models fighting to win a particular data point. And so what we decided to do was to convert all of these objective performances of one model on one data point into battles across different models on the same data point. And there is a lot of science behind that, but I'll talk about it later. So if you take the entire benchmarking setup that we did, it's very simple. You have a large data pool, you have a lot of models, you have a bunch of these rankings, which can scale up very, very well because it's an NC2 over the models, over like different models, over different data points. And what we try to do is we try to embed like useful semantic information from samples. So if you think of benchmarks as like one large data pool that covers many benchmarks, you can basically think of samples as samples itself, not as a member of a data set. So if you're able to extract out as much information from a single sample, as a practitioner, let's say you are super interested in coronavirus in 2020, you have a large data pool which contains many different data sets which solves many different tasks. But you can basically, with our system, you can query coronavirus, extract every single sample that's relevant to coronavirus. It could be immunology, it could be medicine, it could be biology. So there are related concepts or related fields to your query. We extract those samples and then we do evaluations on those samples. So we are allowed to do evaluations across data sets, across metrics, across many different things. And we show that our method is a reliable way to rank models based on this very selective, very flexible kind of benchmarking system. So there are two problems that kind of happen when you bunch together a lot of data points, a lot of data sets and a lot of model evaluations. One, like I said before, is that your metric changes. It's not fixed anymore. A single data set usually has one metric, but when you pool them all together, it changes. And that's a problem, but we kind of abstracted away by converting everything into pairwise preferences between two models on one data point. We convert everything into the A to B preferences, as you can see over there. The other problem, like I also mentioned before, is that if you have this large ecosystem of models and data points, it's very, very possible that you might not have evaluation on every single data point for every single model. And that's not a problem anymore, again, because we convert everything into these pairwise comparisons. So at scale, you will always have a comparison, at least one comparison of every single model that exists in your model pool, which is abstracts away the problem of not having evaluations on every single sample. And before, this was a problem because you can't faithfully compare two models unless you evaluated the two models on exactly the same number of samples. But now that's not a problem anymore because it's just a large arena of battles between models on many different data points. So how essentially we do this is we took inspiration from something in sociology called social choice theory. I'm not too sure if anyone knows this, but I don't really think I have to explain it too much because it's not that relevant. But it's just the idea of assuming evaluation is now an election problem. In elections, you have politicians fighting over voters. Voters choose the politician, and the politician wins the election. Now your politicians are your models, and your voters are your data points. So models will fight for the attention or the victory of individual data points, and that's how you can kind of determine at scale what the best model is. So you write in the best case scenario, the best model would be a model that wins on every single data point on every single data set, but that's obviously not true. So to kind of abstract that away, to kind of fix that, we use a rank aggregation system from the 1950s, which has a lot of priors which I don't think are relevant to this talk. But effectively, if you have a bunch of these comparisons across different models on data points, you can aggregate them as a product of a sum and use an argmax or an MLE to basically get a final model ranking across many, many battles. So this is fundamentally different from calculating the accuracy of a single model on multiple data sets. Instead, now it's more about how many times a model can win against another model. And if you think about, has anyone played chess here? I mean, maybe competitively. There we go. So it's aligned in some sense to the ELO score. So if you think about chess models as chess players and your single data point as a chess match, if you as a very strong chess player lose to a very bad chess or a very lowly ranked chess player, your score goes down much more drastically than if you won against someone who's right after you. Whereas if you win against someone who's much better than you, your score goes up much higher than if you win against someone who's slightly better than you. So we adopt that principle and we kind of use that to do evaluation. And that kind of gives you a kind of a very reliable, grounded in reality kind of model ranking system, which is robust across many different ways. And I'm going to show some results very, very quickly because I think I spoke too much on this one slide.
I have a small question. I don't know if I missed it. How do you normalize for like the different types of games of chess in this setting, right? Like you have different types of data. Like, what if there is more data points in your pool that evaluate a specific capability versus another? How do you normalize for that?
So I would argue that we don't need to normalize for that, and that actually comes a bit later. Okay. Because when you are interested in specific capabilities, then you can subsample from this large pool. So if there are capabilities that are much more well represented, you'll just have more samples in your subset. Whereas when you consider them as battles between different models, the capability that's being tested in the data point doesn't matter anymore. It's more about how a model, like if two models fight, which model gets a question correct or which model gets a question wrong. So for MCQ questions is very simple. Does model A get it correct? Does model B get it wrong? Then model A wins. If both of them get it correct, it's a tie. Whereas for more complex tasks, which are more like, let's say, image captioning, if you have like a rogue score, which is like, let's say 0.1234, and model B gets 0.1123, the one that gets a higher score wins that battle. So it's all of it at the sample level. No. Does that answer your question? I don't think.
I'll read the paper.
Sure. I would say the normalization across data sets don't really matter at this point.
Data points, like different data points, but it's
okay. Sure. Maybe yeah. Sure. Okay. So we had to stress test this obviously, and we had two state-of-the-art like comparison models. One, of course, is your standard ELO score, which is like just the thing that's taken from chess. You start with a score of 700 or 1000, I don't exactly remember what number, and then you go up and down based on that. And so what we do in these particular plots is we try to remove as many data points as possible. As you go to the right of this plot, we show that at the beginning you start at 0, which means the entire data pool is present. And it's not exactly a fair plot, because after 0.9 we go much more granular. So the first half of the plot goes at a delta of 0.2, but afterwards it goes at a delta of 0.02. So we want to show at the extreme cases how stable is our rank aggregation model. So what we compare to a ground truth, and this is the only thing I would argue is not scientifically like very, very good in the paper, is that we have to rely on existing ground truth, which is not well defined. The existing ground truth just being your average across different benchmarks, the thing that we were criticizing before. So maybe comparing, like trying to show a correlation to that is not the best way to go, but it's what we had at the time. And I'm very happy to listen to better alternatives to that. Yes, question.
I think I'm probably misunderstanding something slightly about how this was, how this metric was calculated, because my intuition and expectation is that the variance should increase as you increase the fraction of data missing, at least for the two baseline methods, but it seems like the variance is relatively fixed across missing data fractions. Oh, sorry, the variance is relatively consistent within a missing data fraction, and it's the variance across data fractions that you're showing you're more robust to.
Yeah, because what we're measuring is your final ranking for every single point, right? So we measured it across 4 seeds. So if you have like 2 rankings, we measure the variance between the 2 rankings, not within data points. So it's the variance on your final ranking.
Okay.
Yeah, does that make sense? That's why we kind of show that it might, like for example, if you look at the last 2, the VLM ones, they tend to show a bit higher amount of variance as you go to more sparsity. And by sparsity, I just mean, what if we remove 99% of the data points from your evaluation pool? So this is, I think, a much more reliable thing, because we show that in our paper, we do a lot of experiments to see like what is that frontier, where does it crash? We kind of show that you can get reliable rankings with as few samples as possible. So our aggregation is extremely sample efficient as compared to, let's say, the ELO score, and we just perform better than the main state of the art, which is from LM Arena in Berkeley, right next door. And the only problem is the LM Arena uses like the ELO score priors for their ranking, whereas we use Blackett-Luce, which has this transferability problem. Like we do your classic, if A greater than B and B greater than C, then A greater than C transitive property. So our foundational distribution is different. That's why we are a different metric. But yeah, the core ELO score that everyone loves using is extremely noisy. Don't use it. Maybe it's a bit less like out there for you, but don't use LM Arena's Bradley score, because they use the ELO distribution as a prior. Just use our transitive property, Luce's choice axiom, Blackett-Luce rank aggregation, very low variance, much higher correlation across the board. So if you have more, maybe I should talk about it a bit later, because I guess people are not that interested in this paper, but...
I wouldn't quite say that. I think it's very interesting. But that was a relative order. Yes.
But where things get a bit more interesting is if you have this large matrix of model and data points, like for one model and one data point, if you have this large matrix and you start to randomly remove cells from this matrix, so which is in statistics something we call missingness at random, that is a problem that's still kind of unsolved in statistics. There we show like interesting things happening. We show that the ELO score starts going up I'm an empirical guy. I really don't have a statistical answer to why that's happening, but we do show that the more reliable algorithms start to crash aggressively after like extreme sparsity. So sparsity is a problem, but we still show for both cases of missing data points and missing measurements that up till 95% missingness or sparsity, our rank aggregation method holds fairly well. So the 95 number is a strong number, and we kind of try to advertise it as that. that you can work to 95% missingness.
Is this robust against number of points in the data set? Like, I can imagine if you had like 10 points, 95 would put you at 5 points.
Yeah,
That's
so
going to run into small number.
that's a good question. So we start off the smallest data pool is I think 11,000 data points per Helm. So at that being the smallest pool,
Okay.
stable. And that's kind of fairly representative of how LLM, like the evaluation pool is. So if you don't evaluate on 10,000 data points, don't release the results for your LLM. So that's a small enough scale because it spans 7 data sets. It's not much.
Right.
So if you're not evaluating on 7 data sets, like I mean, what are you doing, right?
Oh, I guess so. You're saying in this dropping is like random across data sets. So like a particular, like let's say 1% of your eval is coming from ARC challenge. Right.
Yeah, it is random. You randomly drop from, but it's obviously a function of how much, like what percentage of your whole pool one data set takes. So it's always going to be a function of that. If one data set has 60% of your evaluation pool, then there will be obviously more samples taken from that one data set.
Right. But in practice, people weight not by how many samples are in the particular evaluation data, right? But by
No, people don't aggregate data sets at all. People just aggregate final numbers.
right.
So
But
my
that's your ground truth that you're comparing against, right?
my ground truth is the ground truth is if you have 7 data sets and you calculate 10 models on them individually and then aggregate those averages and rank the models, that's my ground truth.
Right.
So it's not sample specific, it's data set specific. Yeah. My ground truth is data set specific.
Right. And so if you stratify by data set when you're dropping 95%, would that change these results?
Oh, you mean if I drop 95% of the data sets that I have?
No, sorry. If you drop, so if let's say you have a data set that's 10 points and one data set that's 1,000,000 points, right? And you score models on each of these, and you average the 2 scores. So that's your ground truth.
Yes.
Right. And
yes.
if you drop 95%, you'll drop the 10, all 10 of them.
Sure.
Right? You will completely lose evaluation.
Yes, you will, yeah.
Right. And my guess is that then you would lose some ability to have this. You probably would not correlate well with the ground truth because you've dropped this entire capability. Whereas if you weighted your probability of dropping from the 10 by the fact that it's 10 out of 1,000,000.
Yeah, absolutely. No, you're right.
Would you have a different? I'm curious if you have an intuition around. Is that a good way to go when you're doing this per sample? Because there's sort of this prior, right, that capability matters more. Even though I only have 10 examples of it, I still want to measure that capability. It's kind of like these voters. Yeah. These voters matter more. Like I still care about like Rhode Island getting a.
Yeah. I agree. And this is just to see like how far can we take it.
Yeah.
So we like the point of these experiments. Let's say if we remove 95% of the data points, is to show that like if 95% missingness means you have 50 data points, our method still can give you like a reliable ranking, because when you query something super narrow, you can get 50 data points or less. But we still like this is to show that please trust our rankings. Don't trust the ground truth anymore. So after 95%. Good. And that's exactly what is nice that this slide follows. This is actually the most applicable part of the paper. What we essentially do here is like, since we've collected everything and let's say we want to advertise our benchmarking system to different practitioners. Someone works in architecture, someone works in finance, someone works in biology. And they don't really care, like a biologist doesn't really care how well your LLM will predict the FIFA World Cup, for example, right? So a biologist will care how well it answers questions on immunology. So what we do to kind of allow that to happen is we embed the entire pool for LLMs and VLMs using mini-LM for LLMs and SIGLib for VLMs. And then what we do is we flexibly query random capabilities. In the paper, we kind of just used I cooked up 50 capabilities of my own and I just made a big table out of that. But of course, this is the point of that being is that it's super flexible. You can query whatever you want. And what we do with that query is we align it with all the samples that exist in the pool. We retrieve the top K number of samples. We decide the top K by a threshold, not by an absolute number. So for different models, there obviously going to be a different threshold. For SIGLib, we chose 0.7. If an alignment score of higher than 0.7 exists, extract that sample as a reliable proxy for being representative of your query. And this has been tested by us manually across all 50 of them. So we kind of show that like 70% the threshold, 0.7 threshold is fairly good. And what we do with that is when we have these samples, then we can go back to our ranking algorithm, and we essentially show that if you look at the tab on the right, that we have a lower correlation to the whole ground truth if you sample specifically like this, if you do our querying system. And that's actually a good thing, which means there's a much larger variability in your ranking. So we kind of want to go against this whole notion of one model fits all. That's not true. You'll have one good model for your specific capability, and that's actually something that we should strive for. And that's this whole point of creating benchmarks on demand. If you have a large data pool and you're interested in something, create a benchmark on the fly and run and check which model is the best, and then as a practitioner, use that model as your trusted best model for your use case. So one thing that I really wanted to show, and this actually didn't end up in the paper, is that we have some shared insights with that bench. And the point that I really liked was about discriminability, that there are examples that, of course, most models will get right and most models will get wrong. And those tend to be the least useful models to actually discriminate between, the least useful samples to discriminate between or among models. So we had the strategy of creating this histogram of seeing across these battles for which sample do most models get a question correct and for which sample do most models get a question wrong. And there's this whole spectrum in the middle. And we show with the correlation plot of how good your ranking kind of is, that if you choose samples that have this discriminability power, where like there are certain samples where all models don't get it correct. So for example, let's say there's thought that there are maybe, I don't know, 400 samples where there's the percentages of model correctly predicting that is 40%, which means that there are 60% of the models are getting it wrong. So there's this delta, there's this change that's going on. And we show that if you sample from this pool, which means that these are the samples that have not been fully solved. These are the exciting samples where having battles will actually expose as much information about your benchmarking system as possible. And that's actually a good thing. And I'm very happy that something like this is adopted in that bench. And they also talk a lot about the models that the samples that all models get wrong, which is, I guess, an interesting use case. Samples that all models get right can just be removed because it's saturated. But the samples that models get wrong could either be wrongly annotated or too difficult, or actually doesn't test the frontier. So the kind of work that bench did for the 0%, that the left bar, is actually super interesting, and I really enjoyed going through that. So I just wanted to just name drop it in my slides. But yeah, now moving on to the paper that people actually wanted to get much more in depth with, and I think I'm doing pretty well on time. Yes, so now we move on to pre-training data. We talked about evaluation all this while. Now we talk about pre-training data as a steering problem. So there has been this notion, I mean, of course, this is a paper from many different universities this time, and this is a paper that I presented recently at CBPR. Yeah. So we all know that, I mean, this is possibly the wrong place to kind of make a point out of this, is that, yeah, you need to kind of look at your data. And that's like the thing that I've been doing in my PhD. And I guess you guys know all too well how true that is. But we need to also talk about how filtering is done for data. And I guess you guys do that very aggressively too. The current expected protocol for filtering is something called static filtering, which started very well in the Datacom series of papers, where they showed, let's say for image text data sets at the pre-training scale, that using a strong model such as the OpenAI's CLIP model is a very good proxy to score or rank your pre-training data sets, and you should be able to take the top X% and instead train on that data to get better performance. A couple of problems with that, and the person who came up with Datacom, Ludwig Schmidt, is an author in this paper as well. So the discussion I in fact had with him is that using offline sampling, which means that you curate your data set once and then you train on that data set. And if you have a new idea or a new model that you want to use as your quality model, then you have to curate the data all over again. That causes some problems, which I didn't personally like. So first of all, yes, it's offline and it doesn't adapt to different tasks. So this entire paper is about task adaptability, that there are different tasks where different data samples are useful. And there are different tasks where those same data samples that have been determined as high quality in one task is not high quality in another task. but your static filtering protocol kind of asserts this objective definition of quality, which is something I wanted to question. Like, is it really true? Is that really the way to go? Turns out it's not. Second of all, and this is very specific to my paper because I really focused on concepts. Current static data quality filtering is concept agnostic, and what I mean by that is in this work we really care about visual concepts, or things that we as humans can ground when we see something. And essentially, if we consider the biases of clip models do too. Clip models have an object bias. So instead of constantly complaining as other people do about how it's a problem, we try to like steer straight into that and use that as your proxy. And of course, it is still fairly black box, no matter how well you claim to know your models that you use for filtering. The data or the knowledge that's distilled when you do curation or filtering on these models, those biases end up in your filter data set, and whatever model you pre-train on that will adopt those biases. That's a good thing, that's a bad thing, I don't know, but it's something that exists right now, and I wanted to question it. Yes, so of course, and doing this at scale is extremely hard to control, and the current filtering regimes just outsource the problem to your high quality clip model or whatever quality metric or quality model that you choose to use. So yeah, like I said before, there is no universal definition or notion of data quality. We decided to think of what if we don't discard any data a priori. If we keep the data pool as a high quality data pool, could we find effective avenues for data curation? And that's the entire focus of this work. And I think the next slide is probably the one that I'm going to stay the longest on because there might be a lot of questions, is how do we control that at scale? So to do that, I decided to create or basically augment or create a higher quality version of your data comp original pool, which I call data concept, which in the simplest form is having your data comp pre-training pool, and this is at the 128 million scale. I'd be very happy to do this at a higher scale, but for the purpose of this paper, I kind of stopped at the 100 million scale, is to basically append concept-specific information to every single sample. What does that mean? Is we basically append a list of concepts that are there or can be attached to a single image, as well as their localized bounding boxes for two reasons. One is as a quality assurance regime, which I'll explain a bit later. And the other is just to have more metadata that could be used for tasks that even I didn't think about, for example. So we kind of wanted this data set to be a bit future-proof. That's why I wanted to add as much useful metadata in it as possible. So to very briefly explain how we come up with this final artifact in the middle bottom is we take your standard image text pre-training data set, which is data comp currently, which is just a bunch of image text pairs. We collect a concept bank or a vocabulary, as we like to call it now, across many different sources. So these are like past works, like maybe you've heard of open images, maybe you've heard of the no zero shot paper from like one of my papers, but I'm not the first author. We collect a bunch of these visual concepts, and this is the largest vocabulary that is open source currently. It's about 19,251 concepts. And we use that as our priors or as our proxy to determine what concepts actually exist in your images. So what we do with that, there's a problem that kind of exists if you straight up just go for the bounding box or the object detection model, which is grounding dino, is that if you feed it the entire vocabulary, it slows down inference and also creates hallucinations. So we wanted to fix that because it's obviously a problem. We wanted to have like a very high quality assurance in the dataset because we wanted it to be high quality. So what we did to fix that is we had an intermediate step. So the intermediate step is something we call concept tagging, which basically means we use a model that's called recognize anything, which I'm not sure, let's assume people don't know what that is if you have an image and a huge vocabulary which we feed it, it will return the logit scores or the probability scores of every single member of that vocabulary. So what you can do is you can set a threshold and you can take the top K, you can take every single sample that crosses that threshold and attach all of those concepts to your sample as there is, let's say if a threshold of 0.7, there's a 70% chance that a boat is there in this image or higher. But there's a problem with that. The problem with that is that RAM++ was fine-tuned on their own RAM++ concept bank, which is about 4,500 concepts. Our concept pool is about 5 times larger, 4.5 times larger. What happens if you feed the entire vocabulary to a model that's been fine-tuned on 4,000 concepts? It immensely hallucinates a lot. So and there are additional problems such as you can have a hierarchy of concepts. So if you have Snake, you can also have Python. RAM++ will give an equal probability score for Python and Snake. So even though there's a hierarchy between them. However, grounding Dino has been trained on a much larger vocabulary pool, of course. And our strategy was to basically give as a prompt the concepts that have been tagged by RAM++ as your prompt to grounding Dino. And as we show in this particular example here, and I have a devil's advocate caveat about this, is that RAM++, I would say, wrongly categorized holiday as a tag for this image. But since that can't be localized by an object detection model, that we use that as our quality assurance metric. So since you couldn't localize it in the visual space, we decided to remove that concept, and we decided to stick with the final list of concepts that we show in the final artifact. Does anyone have questions at this point? If not, happy to continue. Yeah, so we basically tag every single sample with all of these concepts. We have confidence scores for them, and we also have the bounding boxes. We kept an unnaturally high confidence score of 0.3 for the bounding boxes, just to be super strict because we're doing this at scale. And in addition to that, we have this concept aware recaptioning regime, where we took an off-the-shelf small-ish Tianwen 2 model, and we fed it the alt text, which is boat on choppy waters, because it contains a bit of world knowledge that humans kind of add to it. We don't want the data to be purely synthetic. A good example, maybe a better example would be, let's say, boat on choppy waters in Switzerland. So if you just feed the image and ask it to recaption it, it's highly unlikely that non-frontier models will be able to detect that this is indeed Switzerland. So using the priors or the proxy of the alt text, you can kind of distill world knowledge or human added valuable information into your final caption. And we also feed it the list of concepts, so we wanted to be more concept adherent. And some general statistics is 128 million samples. There were only 12,000 localizable concepts from the 19,000 pool. So there has been about 7,000 concepts that would not be localized properly, and I think it's fine. Until we have better detection models, let's stick with 12,000 concepts, which is, I would argue, a fairly good representation of the world visually in terms of concepts. And across all of these 128 million samples, we have about 500 million annotations, which is a median of 3 concepts per image. So I would argue that the dataset is fairly representative of visual concepts and kind of complex. And some statistics that might be useful as data people for us is that on the right, we show that even though the median number of concepts per sample is 3, there is a very long leftward push, and the long tail ability is very, very strong. The skew is extremely strong. So most images are actually simple, and complex scenes are a bit rare. By complex scenes, I mean like just objectively in terms of concepts. If an image has more than, let's say, 3 or 4 tagged concepts, I would call it a complex scene because it describes something a bit more visually complex. And on the right, we show extreme long tail in terms of concept distribution. There are about 186 concepts that have more than 1 million images in which they are a concept, let's say. And the top 5 concepts are man, woman, flower, car, and wallet. So it is extremely, extremely long tail. Wallet, surprisingly.
I feel like the first 4 make a ton of sense in terms of what people care about. Man, woman, flower, car. I would pick like dog or something, but like wallet.
We have the list of the top 100 in the paper in case you want to look at it. And there's this very, very aggressive long tailness of your concept distribution as well, which actually tells us that your data sets are very, very biased towards, common concepts or things that are like, it's just a reflection of the data you have. So maybe people should take care of this when you want to curate better data. And the captioning is a bit complex as well, in the sense that your captioning is very left skewed as well. Most texts are very small, but with our recaptioning practice, we kind of try to flatten it as much as possible. We also show that the alt text doesn't adhere to concepts, which is the 3.8% exact match. We improved it a lot by the exact match of 51%. And if you relax the threshold a bit, we can go as high as 87% if you do partial match or fuzzy matching across concepts on the text space. So that's good. Our data set is actually quite strong in terms of captions, in terms of the concepts that you add to it. Now, what actually, maybe if people are interested, there are some qualitative examples. We show good concept adherence. We also show that it follows alt text when it matters, and doesn't follow alt text when there's just random garbage in the alt text. It's not shown here, but again, it's in the paper. But actually, what's interesting for this particular talk and what's the main core focus of the paper is that if we have these concepts, how can we curate batches that we feed to the clip model at training time? And to do that, I developed this very, very flexible algorithm. This is probably the most technical slide of the entire talk. So just to give an understanding very, very quickly so that I can finish in 5 minutes, is that if you have a larger batch of data, batch sampling basically takes, let's say, if we work with 10,000 samples, we want to distill it down to, let's say, 1,000 samples. We have a larger pool, which we want to condense to a smaller pool. And there should be many flexible ways to actually determine what those 1,000 samples that are fed to your model are. And that is what we call H, your concept-aware heuristic gain function. That is extremely flexible, and this def caps function is meant to adapt to whatever new heuristic function you wish to define. I have worked on 2 in this paper, but of course you can create anything on the fly. And the nice thing about it being online filtering is that you're not distilling or creating a final data set before training. This is happening during training. So if you wish to do curriculum work, if you wish to change your heuristics midway, it's super easy to actually do that. So the 2 things that I tried to do in this work, one was, let's say, optimized for classification, and one was optimized for retrieval. This is similar to a recent blog post from Datalogy from last year, which I found really, really cool. I tried to add more details into how we did that curation, which of course you guys can't make public. So what we decided to focus for classification was, if you think about a good classification model, it should be able to distinguish or make distinct in the embedding space many different unique classes, right? That should be a good end goal of your classification model. So if you think about it scientifically or theoretically, a great way to actually do that, if you have, let's say, concept level tags for your data, for your entire data set, is to max out as much as possible the number of unique concepts you see in the batch that you feed to a clip model at every time. So we decided to do just that. So I can, of course, go into the algorithm itself, but in brief, as a TLDR, that's exactly what we did. So one interesting thing we did was we observed, of course, you saw that super long, the long tail skew of your concept pool, which means that there are the vast 95% of your concepts are extremely rare in your data set. So we decided to have, that's the only thing that I would like to make technical about how we did this, is we had a rarity bonus module for your scoring function. So if you collect a sample which has a rare concept, which we determine before training, just as a function of the entire concept bank or the total number of concept annotation, if a concept is rare by a specific number, we collect that frequency of the number of times it exists in the entire data set, and we do the inverse of that. So we basically want to upsample samples that have rarer concepts to be thrown into your final batch at the beginning. This actually reduces training time by quite a lot, instead of if you were just to randomly pick up samples and then basically create a counter of the concept that have been seen so far and only stop looking at specific concepts when you hit a cap. But if you were to upsample your rare concepts first, the score that you assign to samples with rarer concepts gets thrown into your batch earlier, which kind of means that you can fill up your 4096 clip batch before you hit your cap of, I don't know, 20,000 or 30,000 or even 50,000 number of samples in your larger batch. So what that I'll show later how the distribution looks like, but that's basically what we do to optimize for classification. What we do to optimize for frequency is actually much, much simpler, and it's kind of really stupid. Is you take your larger batch, you see the number of concepts, you see the total count of concepts in each sample, And of course, we wanted to argue that retrieval data sets have relatively more complex visual information than your classification data sets. What does that mean? Is that like if you were to match a text to an image, usually Coco, Flickr, these data sets are more complex in nature compared to classification data sets. So our curation was super simple. Take a larger batch, count the number of concepts in each sample, rank them in decreasing order, and take the top here. So that we show later that it works really well in terms of performance. But in terms of distribution, what's actually interesting is this task adaptability push that we're trying to make, in the sense that if you take your diversity maximization and draw a histogram of it, and if you keep your x-axis as, let's say, in your sample, how many concepts there are, our argument is that classification data is much simpler in terms of the number of concepts in them, but the diversity of those concepts are immense. So we show that there's a left-leaning skew for your classification optimized batch, and it seems to it. And if you take the ImageNet training set and you do the same data concept style annotation and you create a batch and draw histogram, there's almost a perfect overlap between your ImageNet training set and the batch we curate from Datacom. And we do the same thing for the Coco training set, and we show a very similar trend. So it turns out that without actually optimizing for these two tasks, we seem to have a fantastic distributional match for both of them.
It's like eventually like a target distribution matching in some way.
Yeah, exactly. But we didn't know.
The priors match up.
Yeah, the priors match up. So it was fun. Just one last point about the classification optimize. If you randomly create a clip batch, your concept distribution has this long tail. So you'll have man and woman as your most populated examples, and they kind of take up the majority of the batch. But with our thing, when we created a cap of 40 instances of one concept, your batch is much flatter. So that kind of forces your diversity. And we show that we almost just 1.7. We have 1.7 times more concepts in our curated batch than if you were to take a randomly sampled batch. So that's good. We have higher concept coverage. We have a flatter histogram, and of course, more rare concepts get thrown into your batch, which is a good thing. And they have a relatively equal weight to your more common concepts, which levels the playing field. These are just results. I wouldn't publish a paper unless we had good results, of course. So maybe these slides aren't that important. What we do show is that we evaluate on 28 benchmarks. There are two retrieval benchmarks and 26 classification benchmarks, which I can show you in the next slide, which includes a vast diversity of data sets. Some are very, very long-tailed. We even evaluate on an extreme case of long-tail classification data set, which is called Let It Wag from one of my previous works, where we took the most long-tail concepts across all the benchmarks, and then we evaluate on that. But we show good performance on CLIP, SIGLIP, on our recaption data, across the board. We tried different model architectures, we tried 2 different captioning methods, and we show the trends are very, very strong across the board compared to random sampling. But how does it compare to other benchmark works? We compare with Metaclip. Maybe everyone knows Metaclip here, but Metaclip basically does offline curation on concepts but on text, and we argue that's very bad because, first of all, their vocabulary for text consisted of prepositions for some reason, which I didn't really like. It should be done on nouns because that's how you do better alignment with the visual space. But what we did to make it apples to apples was we basically did an offline version of CABs. The left plot is to basically show that online sampling is better than offline sampling. So Metaclip for CABs is basically an offline version of CABs. We just curate the data set offline and then we train on it completely. And this is the only experimental case where we do better on every single benchmark. In some other experiments, we do worse on 2 or 3 benchmarks, but this is the only case where we do better on everything, which is, I think, cool. We also compare with 2 other online sampling methods, but they haven't really caught up to scale. Other online methods kind of use the model as the decider for your batch. So they go through multiple iterations or multiple epochs, and they fix the model performance or the model weights at the end of one epoch to inform the batches of the next epoch. This doesn't really work at scale. So if we again try to adopt that regime, we show that the online methods kind of do at par with if you were to just randomly sample data points just randomly. So which means that all of that extra computation that's used to decide your batches doesn't have any effect essentially. So what you need to do is you need to use caps. The last result is, what if we were to train longer? The plot on the right. So if we currently train for 128 million samples seen, but what if we were to take the same data set and train it to the billion scale, which is a bit more realistic, right? What we do show is that if you were to use our method, we show like a much larger gain at the beginning, at the initial stages of training, but it starts to plateau as you go towards more repeats of samples, and as you go towards your at the end of your training stage for 1.2 billion samples seen. To be noted that IID never really crosses our method. Maybe it's not very evident from the plot, but we train for a bit longer. It never really crosses, so rest assured that our method works. But the way to interpret this plot were to let's take the vertical line, and if you just take the point where it hits the green plot and you extrapolate it to the gray plot, that means that is your compute multiplier. So at that much less compute, which means that at, let's say, 30,000 steps, the performance we get matches IID performance at 100,000 steps. So that's like a 3.33 compute multiplier. So our method at the starting stages for longer training regime is 3.33 times faster to get an equally good performance, which I think is a good result to show. And yeah, we've done a lot of ablations across different filter ratios. So could you take from 20,000 to 4,000? Could you go from 40,000 to 4,000? Could you go even higher? We tried different cases. We saw the best performance at a 5-time reduction, which is a filter ratio of 0.8. Longer training really works. And we also did cabs on top of a clip scored filtered pool. So if your data is already high quality, can online sampling actually help? Turns out it can. It does fairly well actually. And like we did a bunch of empirical results to show that on both online sampling and concept-aware sampling are actually good for curating, our good curation methods, and maybe people should actually work on that. I would stop here as my last slide and would throw open questions at everyone. These are the things that I still haven't really gotten through to answering properly. For evaluations, other aggregation algorithms, for capability probing, is there a scope? Because I just came up with it myself on the fly the night before ICLR. Is there a way to have queries that fight each other? Is there one task where there are many queries, where there are different models that do well? What is the best way to use different models when you have this evaluation protocol from one bench? And how does one bench or these kind of sample level evaluations adapt to longer horizon tasks, which is actually the reality of our evaluation right now. Our tasks right now are much longer horizon. We solve many different problems, use agents. There are many different things that have happened in the last year or year and a half in evaluation. Will my method hold up to the future? I don't know. Maybe it does, maybe it doesn't. These are some open questions. And for VLM pre-training, even though it's a one-time annotation problem, is there a cheaper way to get as high quality annotations? How do we leverage this data set beyond contrastive training? I'm fairly sure it can be used for autoregressive, and that's something I'm working on right now. And is there what are good protocols to densify supervision, like I did in this case, for other modalities? So these are some open questions I've had, and maybe this is the slide to stop at, so that if people have questions, maybe we can all have like 5-minute question answer session if you wish. Yeah. But yeah, thank you so much for inviting me. I hope this was a useful talk, and I'm very happy to answer as many questions as you have, one-on-one or right now. Thank you. Bye.
One question I had was, like, I guess there's a diversity element and a concept quantity element, and I guess one of them matters more when you're doing contrastive sampling, but potentially not as much in autoregressive sampling. Or would you expect diversity to matter there?
I mean, you're absolutely right, because in CVPR we had a rebuttal, and it was a very stupid question to ask because this is a clip paper. They said, why don't you evaluate on image captioning? Okay. I'm like, instead of arguing that this model literally can't generate text for you, I said, just do it myself.
Yeah.
And turns out that we did image captioning datasets as well as VQA. And turns out the diversity maximization thing, having a vast diversity of concepts, turns out it performs better on every single thing. So for example, we did retrieval on Coco, and this the FM, the frequency maximization thing works better. Turns out the diversity maximization does better for image captioning as well as VQA. So I think if there is a protocol to use for autoregressive models, which actually people care about, do diversity maximization.
And is that in the batch or is that like just in the data set itself?
No. You mean this autoregressive?
Yes.
I just took the checkpoint. It's your standard Lava fine-tuning
The
regime.
backbone is so much better that it helps everything. Okay.
It doubles performance compared to IID,
Interesting.
even for like tougher benchmarks. Yes.
Why do you think the performance saturates here after extending training very long?
Sure. Yes. Great question. It's a problem of repeats. So basically, if you take our batch, if you look at it in the worst case scenario, our batch sampling algorithm, when you distill down 5 times, in the worst case, we'll see 5 times more samples than your IID batch. So, which means that for, let's say at one epoch when it's over, your CABS algorithm sees 5 times more samples than IID. So that means that at the end of training, there will just be 5 times, and yeah, of course, because you're training 10 times longer, the worst case could be 50 times repeat for certain samples. Does that make sense? I could elaborate more.
Yes.
Maybe I didn't explain it that well.
No. That makes sense.
So the repeat is a problem, and the way to abstract that away is to scale the data. So if you scale the data, if you do this annotation, you do CABS on, let's say 1.28 billion samples, you do for that data set, and you train for 12.8 billion samples, I feel like that problem will get abstracted away slightly. This is a problem scale.
Makes sense.
But would you think that if you expanded the pool later on, would that reduce the performance, or would that,
If you expanded the pool,
like let's say you made the filtering like less aggressive in the future batches, would it like gel with the initial sample, like, or would you actually expect it to plateau?
Actually,
Like for instance, like you train on the high quality data first, and now you're putting low quality effectively later on. Versus like aggregate distribution.
I mean, there is this line of research, I mean, from you guys as well, that quality of data at different stages of training matter a lot, right? Probably you need higher quality data at the beginning of training, and then if you've made a really good model starting to plateau, at some point maybe like more general diversity could actually help. Like let's say general diversity from lower quality samples could actually have benefits. This is not something I've tested. People have said like we want to do a follow-up using curriculums. I said like guys, do it. I'm going to do autoregressive stuff now. But this is a very cool point, and I think it really should work. Having like a difficult to hard or like some regime or a curriculum would benefit performance. But my professor really hates curriculum learning, so he said don't do it. I'm like, if there's one time a year I listen to you, it's this.
Yeah. I tried hard to easy, easy to hard, and everything worked the same as random.
Really?
I don't know if it's promising or not.
Okay.
I came with the same amount of ambition. But I've been burnt in the same experiment.
There was an experiment that never ran through. I think that I didn't even check if there's a checkpoint, but I did try like a slurp style of interpolation from how you change the filter ratio with time.
Yeah.
There is a checkpoint. I haven't evaluated it even because I just moved on. But maybe I could go back, evaluate, see if it actually works or not, and then I can get back to you. Cool. If anyone else has any questions, we can talk now. We can talk later.